This video is part of the series on the Control101 MATLAB toolbox. This particular video focuses on the house temperature app files. So the community has agreed on an outline structure for a Control101 course. And the MATLAB Control101 toolbox has been developed to support such a course. This is because MATLAB tools enable visualization and support tedious number crunching requirements so students can focus on core concepts. So in this video we're going to focus on a house temperature system subject to numerous possible sources of uncertainty. So let's consider a house which has controllable heating, which is shown by this red rectangle, so more heating and the rectangle basically gets bigger. An uncontrollable and randomly changing external temperature, so that will give you heat loss. A randomly changing wind, which will also affect the heat loss because of wind chill effects. And the house will also be defined by its size. So the size basically links to thermal inertia, and the wall thickness, which links to heat loss, how quickly heat will escape from the house to the environment. The colour of the house, here you can see it's blue, is used to indicate temperature. So we use blue for cold and red for hot. So the first app then, house temperature behaviour. A core learning outcome is to understand the behaviour of the house. For example, how fast does the temperature change? If you're in a house, you want the heating to heat the house up quickly enough so you're comfortable. What is the steady state? Is it, again, a comfortable steady state temperature? What is the impact of changes to the heating, to the external temperature, and to wind speed? And what is the impact of changing the house size and wall thickness? So the house temperature and behaviour app allows users to explore these questions and check the answers accord with their expectations. So let's do a live demonstration. So I'll find the house temperature app. There it is. Again, you sometimes have to wait a few seconds for it to open. You can see the manual is being opened automatically, as you expect. So there's the manual. If you want to look at some of the engineering background and some of the source MATLAB code you might use to investigate, it's all there in the manual. So here's the app. Okay, now what you can see is you've got in the yellow box two sliders you can change. One's the size of the house, so basically the thermal capacity, so you can have a very big house or you can have a small house. And heat loss, you see if heat loss is low, you'll see it makes the walls very thick to say you're well insulated. If heat loss is high, you can see now the walls are very thin, so heat escapes very easily. So you can change those parameters. You can change the heat supply, so you see it changes the size of the rectangle so you get an impression of how much heat you're supplying. Change the external temperature, so that tells you basically you might notice the house changes colour. How cold do I start? And change the initial temperature as well. So now we can press simulate, and again the first time it runs sometimes you get this funny effect where things don't appear perfectly, but after that it's usually much better. Okay, so you can see the response. Now you might want to say, what happens if I make the heat loss a bit bigger? So I've made the heat loss 6, and let's run again. And you can see you get a different temperature profile. Okay, what happens if I make the house much bigger? And you can see it's slower to rise, but you get to the same steady state. Okay, what if the external temperature is different? So let's make the external temperature a bit higher. And then you see, well, basically, because the external temperature is higher, the heating is able to take me to a higher internal temperature. Anyway, hopefully it's obvious what all these sliders allow you to do. The final thing to note is if you get fed up of waiting for the animation, you can switch the animation off, and then you can do basically instantaneous changes and investigate much more quickly. Okay, so we'll close that and we will move to the next example. So We've already talked about the manual, so we don't need to say much more there. It basically has the underlying explanation in engineering so you can understand what's going on behind the app. Now, the house temperature storyline app. It's important that students understand the entire control design process. So first we analyze open loop behaviors and understand where and how feedback control is needed. And you'll have seen that in that example we've just done. Did you get to the temperature you actually wanted? Second, we form mathematical models to capture the system behavior. After that, we evaluate manual or open loop control. Will these be adequate? Because they're simple, so always the best options if they're good enough. Next, we undertake systematic model-based control design, and here we illustrate PI. And finally, we want to evaluate the closed loop performance in a realistic scenario with uncertainty and disturbances. So the Storyline app allows you to go through this process with tabs that direct users to each step in a sensible and systematic manner. And again, the manual will give you more discussion and detail if you need it. So let's do our live demonstration. We'll open the app. There it is. So I'll just move it across from the other screen. So as we explained, you can see at the bottom here we've got the 5 tabs. So I'm going to switch the animation off so we don't waste time. So first you have the open loop behavior. So you can simulate and see how does the system behave, and that's like the one we just did. Here you've got the wind, so you can say what happens if I change the wind? What impact does that have? And you can see it's changed the behavior. What if you get the wind only to change mid-simulation? Okay, and then you can see when you introduce the wind, it basically has a wind chill, so it reduces the steady state. What about the external temperature? What if that changes mid-simulation? Okay, and again, what you see, you change the external temperature mid-simulation and you get different behaviors. So you can explore the open loop behaviors with the first tab. The second tab, open loop modeling. So now what we want to do is basically model the system as a first order model and find the time constant and the gain. So this app allows you to go through that process, check you understand, and for a specific system you decide your heat loss coefficient, your thermal capacity. Can you find the time constant? Can you find the gain? So you've got your model now which you're going to use going forward. Now manual control. So manual control, basically you want to try and get a particular desired temperature, and you'll see that's marked with this dotted green line. So I'm going to choose the heating. Okay, so basically I can change the heating, and you've got to ask yourself, am I getting to the desired temperature? And you can see here I'm beginning to rise, but it is fairly slow. Okay, now at the moment I'm including changes in external temperature and changes in the wind, but if you look at these sliders, these both have been set to 0, so nothing is going to happen. So what I'm going to do is end this simulation, okay, and I'm going to introduce wind and an external temperature. Okay, you'll see the wind is represented by these, wind velocity by these green arrows. So now I will get random changes in the external temperature and random changes in the wind, and they will be denoted in this figure down here in the bottom right. And when these random changes happen, you will see they have an impact on the temperature. And so your challenge is, can you actually get the temperature to the desired level with all these random changes going on? So they'll start occurring shortly. It's running quite slow. It usually runs a lot faster, but probably because I'm running a video. So here you can see there's been the first random change in external temperature. It's gone from 0 to 10, and you can see here's been the change in the temperature of the system. So the question you have to ask yourself is, can you get the system to target. Now, I've cocked up here, but this is only illustrating what you can do with the apps. The total maximum heat supply is only 20 kilowatts, which is quite low, which is why I'm struggling to get to temperature quickly. And maybe you might think, well, that's quite informative. But hopefully you see the point. So you can manually change this heating, and what you've got to try and do is keep the temperature at this green line while all these random disturbances are happening, and you'll quickly discover it's quite tedious. So I'm going to end that simulation and move on. So when you've realized that maybe manual control is not a good idea, you can try PI. Okay, so the next tab oh, I forgot to refresh the screen, apologies. So it allows you to investigate PI. So you can do things like change the integral. This is probably not a good choice. So you can see, well, maybe that's not a particularly good PI at the moment, but it's doing the job. It's rejecting the disturbances, it's rejecting the wind, it's getting me to the right temperature. Okay? Now, once you've basically tuned your PI, and you're saying, I'm happy with that PI, maybe I'll just reduce that I a bit, what you want to do is evaluate it in a more sensible scenario. So the final tab basically includes all these different types of uncertainty. You've got wind effects, which will come on and off, measurement noise, which will come on and off, measurement delay, which will come on and off, and changes in the external temperature. So if I press start, then what you should get is basically random changes in all these values. So this bottom right figure tells you what the values are for all these different types of uncertainty. And then your control law, which you've tuned in the previous tab, is going to try and get you to 20 degrees. And you can see the input that it's saying that you should use here in the blue line. Okay, now this red line, this noisy line, is showing you the actual measurement, and the blue line is telling you the real temperature. Okay, now at the moment we haven't got any delay, but when the delay comes in, you will see that these two lines begin to differ a bit. They tend to start moving apart. So I don't know when the first change comes in. This is running quite slow, but when the change comes in, you will see, because there will be steps in this bottom figure, because all the values have changed, and then you'll find the control law is going to have to start working harder to keep you to the required temperature. So I think it's going to change very shortly. So you may find this runs a lot quicker on your computer because I'm recording a video at the same time. I think it might be causing it to lag a bit. So there you can see the changes. Okay, and now you'll also see this difference between the blue line and the red line, and that's because there's a delay in the measurement. So you think the temperature is the red line, it's actually the blue line, and that impacts on the efficacy of your control, which you can see here. So the whole point of this app is allow you to investigate how does real uncertainty affect your behavior. Now, what I can also do is if I click this PI button, you'll see there's an alternative of on-off control. So on-off control is switch the heating on if it's too cold, switch the heating off if it's too hot. So you can see here you've got this on-off mechanism going, and you can also investigate how effective is on-off control, because it's a very simple control system. I think that's enough. Okay. So we've demonstrated how to run and use the house temperature apps in the Control101 toolbox, and these can be deployed during lectures and student private study to help students appreciate and relate their technical and analytical learning to authentic systems. And they can also be used to support pre- and post-laboratory activities, especially those related to heating and temperature control equipment. The manuals, which open automatically, contains some of the MATLAB source code that can be used as templates for individual investigations and modifications beyond that allowed by the apps.